All right, good afternoon, everyone. Thank you for coming to the Food Safety Educational Conference. I am Morgan Madison. I will be your moderator this afternoon. I work with Florida Fruit and Vegetable Association. I would like to introduce our first speaker, Chris Callahan from the University of Vermont. I'll let you pull up your presentation.
Hey, good afternoon, everybody. My name is Chris, and as Morgan said, I'm from the University of Vermont. I work in extension there. I'm an agricultural engineer and spend a lot of time working with growers around post-harvest challenges related to food safety, but also efficiency and especially labor efficiency. And so one of the things that I've spent a fair bit of time working on is hygienic design. And that's what we're hoping to get into today. So let me see if this is open yet. I barely know anybody, I think, in this room. So if you could help me understand who's here, that'd be great. Show of hands, how many folks are growers? Great. Any equipment manufacturers? We missed them again. What about extension? Regulatory partners? Hi, Diane. Okay. What am I missing? Does that cover it? Trade associations, of course. Thank you. What a great conference. Cool. Thanks. That's helpful. So the title in the conference proceedings or the agenda was Welds and Whatnot, which I think is a great way to think about this. It really is a sort of an easier way into the topic of hygienic design or sanitary design. Like I said, this is something that came up because of my work with growers and constantly trying to think about when you're told you have to clean and sanitize something as necessary and appropriate, that's a very easy thing to say. It's a very difficult thing to do oftentimes, and so we chose to jump in with growers and think through what that actually looks like in practice. A lot of this work is informed by standards that exist in the food manufacturing world, but which were generally pretty intense or a little bit more detailed than we thought was appropriate for most farms and packing houses. And so a lot of this work came from translating that into produce farm context. So what is hygienic design? The idea here is that we're being intentional about designing or retrofitting or improving equipment or spaces so that they can be cleaned and sanitized. So who loves when something is clean? Okay. Who loves doing it? What gets in the way? What's the difference between loving when something's clean and actually doing it? Oftentimes it's not designed to be done, right? Like there's stuff that gets in our way here. And so this practice is meant to be the antidote to that. It's a series of practices that help bridge the gap. And so at the root of this practice is the idea that microorganisms, I don't know how many folks were here in the morning portion of the session, but we spent a lot of time talking about all the different ways microorganisms, particularly human pathogens, can survive and reproduce. And one of the things they really like are small places with just the right conditions, and oftentimes our equipment and packing houses can provide that. And so what we're looking to do is make sure that we're designing features into equipment and the buildings to minimize or eliminate those harborage points or places where human pathogens can survive and reproduce. I want to also say that this is a half-hour presentation. All of these materials that I'm going to be referencing are available for free on our website. If you go to go.uvm.edu/hygienic design, there's also a video series of this presentation in its longer format. I'll be talking about a couple of checklists that are available to help do this on the farm and things like that. So that's all available there. So hygienic design really, in our mind, comes down to 5 key principles. One is that all surfaces are visible and reachable. That doesn't mean during practice and during production, of course, right? We want to make sure we're also protecting human safety, not just produce safety. But eventually things need to be visible in order to be cleanable. Then if they're visible and reachable, we need to make sure that they're smooth and cleanable. And so there's a lot of active work in this area looking at different materials and different surfaces to improve their cleanability and to better understand their cleanability. Sometimes it's not completely intuitive. The other thing we try to do is, number 3, try to avoid collection points. So these are places where organic matter can accumulate, where you might end up with biofilms, like we talked about this morning, where human pathogens can survive and reproduce. The 4th thing is thinking about compatible materials. Not only compatible to the main use, but also compatible to being cleaned and sanitized. So painted iron, for example, is a common, or painted carbon steel. Oftentimes paint will peel off and things like that. So thinking through what more compatible materials might be. And then the 5th one, I'll admit, is a bit of a catch-all. Preventing contamination seems obvious and seems broad, but actually taking the time to think about, when standing in front of a particular piece of equipment or a line, where are the places where contamination can occur around the line? Can be a really helpful activity. So let's take these one by one. Visible and reachable surfaces. I also want to say, all these photos are based on farms that I work with. You may have different kinds of equipment, different scales of equipment. I'm happy to talk with any of you after the presentation about specific pieces of equipment you have. But I think that the fundamentals still apply. So visible and reachable surfaces. If you can't see it and you can't reach it, what else isn't going to happen? Can't clean it, right? So, right, you can't clean it, and if you can't clean it, you can't sanitize it. So this is a good example of it's a brush washer. Maybe some folks are familiar with these, used a lot for root crops up our way, but also apples, some tomatoes, peppers, etc. And so there's a series of brushes inside. It's covered because those brushes have water also being sprayed, and so you don't want the water getting everywhere. The downside of that is anytime you enclose something, it becomes more difficult to actually see what's going on in there. And so you can see the corner in this bottom photo, the far corner, of course, not getting cleaned because it's not often seen. So thinking through how you might gain better access to that and look at it on a more regular basis and clean it. This is an alternative to that. This is an AZS rinse conveyor, and so a couple of key differences here. There are no brushes here. This uses water pressure to do that cleaning step. It's designed so that the belt can be accessed both from the top but also from the bottom, so that the whole thing splits and lifts up. Made by the same company, about a decade of difference between the two in terms of standard manufacturing and design, but just as an example of how things can change over time. The other thing that can help with access and visibility is this idea of toollessness. So if you find that you need to remove a panel or something to get at a specific section of a line or a piece of equipment, it might make sense to convert that into something that doesn't require the rare half-inch wrench that one person has in their back pocket, 5 miles away. So something you can replace, maybe a bolt with a knurled nut or something like that, if it's something you need to get at on a regular basis. It's also really important to remember that we follow something called lockout, tagout, or common sense to take away power from these machines when you're working on them, things like that. When we're cleaning and when we're gaining access to places that are often protected, we want to make sure the thing can't turn on. This is an example of just one of these types of panels where on the rinse conveyor I showed before, there's a section of the belt in between the top and the bottom that is really hard to get at. And so this is a panel that the manufacturer has included, and you can see that it's 2 wing nuts that you take off. You really just loosen them. That's the other nice thing, is anytime you can have something that's captive, you can loosen it, but it stays on. That's great. And so you just loosen these, that panel lifts up, and you can gain access between the belt. So toolless access to an area that they know is going to be hard to clean on a regular basis. The second principle of hygienic design is smooth and cleanable surfaces. And so, again, we want to make sure surfaces are smooth and cleanable so that we can really, first of all, know whether or not they need to be cleaned visibly. We can visually inspect and see whether it needs to be cleaned, but also that we know when it is clean. when it gets clean. And also that detergents and sanitizers can be effective. Oftentimes sanitizers, when we look at the label, only have a labeled use for hard, smooth, non-porous surfaces, for example. And so making sure we're using them on surfaces that they're meant for. Some of the challenges we've run into, I don't know how many folks have seen washing machines used as green spinners, for example. We have a lot of farms that do that. So we've spent some time actually developing some standard operating procedures for that type of use and specifically for doing the conversions in a way that makes them cleanable, and then standard operating procedures for actually cleaning them. This is another piece of equipment that's actually very, very common among small diversified growers, especially for root crops. It's a barrel washer. Anybody familiar with these in the room? A little bit, okay. And it's a good example of just taking a pause in a presentation like this and say, what do you all see based on what we've talked about so far in terms of visible and reachable surfaces and smooth and cleanable surfaces? Porous? What's porous? So the wood is going to suck everything and anything into it. Thank you. Yep. See if I can get the pointer here. This gap, where you have a round hoop coming up against a flat slat of wood, could be a niche or a harborage point. What else? It might be hard to see, but what's behind the fence? Never mind, we're moving on here. There's nothing behind the fence. No. Adjacent uses, but this is getting to the number 5. In this case, it was some pigs, but so let's just keep that in mind. Adjacent uses and potential routes of contamination. The other thing that happens is sort of unintended consequences, and so wood, scary wood. Let's not use it. It's porous. It's going to absorb everything. Let's switch to stainless steel. Cool. Right. So we switch to stainless steel, and the carrots just sort of wallow in the belly there, and they don't tumble like they did with the wood. And then so what do? Let's add some carpet to kick the carrots up. Right. Now, this is a really extreme example, but I got to believe everybody on your farm has something like this. Right, some retrofit that was made to a piece of equipment because those knuckleheads don't know how to design what we need, right? And so we made an adjustment, and you had to make the adjustment. Are there any unintended consequences when it comes to cleaning and sanitizing? This is an extreme example, but it's worth thinking about the changes we make and how they might impact cleaning and sanitizing in ways we don't expect. It also brings up the other point of a lot of the things that benefit hygienic design for produce safety can also provide real quality, product quality benefit. So thinking about plant pathogens and bruising as well as human pathogens. For example, so 2 apple lines. The one on the left has retrofitted some carpet onto the fences to prevent bruising, right? And so it's soft, but it's also absorbent and hard to clean. On the other one, we have pool noodles that have been cut in half and put on the fences. Let's compare these. The carpet is stapled to the fence. The pool noodles are split down the center and put over the fence. Pros and cons? Say again? The carpet is brand new every day. You're right. No. Yes, but they are washable. So they can be removed. You can gain access and potentially wash them. You have an option. With the carpet, not so easy, right? So there's a continuum here. The other challenge that we often run into are these donuts, these drying donuts on the end of lines. Often, and these are varieties of foams that are used in doing this. There's some active work looking at alternate foams that might be easier to clean. The other thing to sometimes think about is replacing these. Has generally been the standard, replacing them as you see wear, as you see soil build up, etc. or on a preventive maintenance schedule. This is another alternative. I don't know if anybody's using anything like this, but I saw this recently. It's a drying belt, and so it's a porous belt that on the top, this part right here is a blower. It's an air knife that blows high velocity air down, and underneath it is the vacuum side of that. So it's pulling the water off. So there might be some alternatives to what we've typically done. Fundamental number 3 is no collection points, so avoiding niches, sandwich joints, lap joints, flat or concave surfaces, etc. And so the title of this talk was Welds and Whatnot, so this is where we're going to talk a little bit about welds. In the upper right photo, we can see a couple of welds that were done to assemble this piece of equipment, and on the lower photo, we see a different kind of approach. So what's different between these two, based on what we're talking about? I can't hear you, sorry. Yep, bottom one's more cleanable. Why? Yep, so this is actually a bend in some stainless sheet metal, and then the only weld is right here. And the weld is continuous and smooth. Whereas these welds are pretty rough. They definitely serve a structural purpose. They'll keep it together. But in between them, we've got a joint, an open joint between two pieces of metal where water can get, where organic matter can get, and where we might be harboring some pathogens. So trying to avoid that. Ways to do that as a retrofit, you could definitely hire in some welding. You might also be able to seal it with some silicone as a temporary. Yes, ma'am. No silicone? Okay, thank you. So no silicone. The concern is that water can get behind it and stuff can live there and it peels off. I'll go with that. Thank you. Anything else? So if you don't do silicone, what have you done to fill in welds? So I'm going to try to summarize that. Thank you, first of all, for contributing. I'm going to try to summarize that. I heard weld it with a continuous smooth weld, if you can. The other option would make it a focused area of deep cleaning on a scheduled basis. The other thing, too, are there ways to make sure that it doesn't accumulate water and can dry between cleanings? So, anybody have anything else to add? So this is an alternative to the barrel washer we talked about earlier. This was one manufacturer's attempt to do away with wood, and so it's polycarbonate plastic, and you can see a little bit more here. Again, that has, while it's smooth and cleanable, it doesn't necessarily support the tumbling of carrots and other root crops, which was necessary for this type of washing equipment. And so they put in these slats to try to promote that tumbling. And, so on the one hand, it's a smooth, cleanable surface, but you also end up with a few more joints that need to be cleaned or have the potential for harborage. And so what might we do, trying to think back to the other fundamentals we've talked about? We have some slats that have been attached to the side of this barrel. We know that they're going to accumulate stuff underneath them. Right now, they're on there with nuts and bolts. Change the hardware. Make it so that this stuff can come apart on a more regular basis for a deep cleaning, for a complete drying after being cleaned, is one way to address that. This is another example of some adhesive foam that was put on as a retrofit on a sorting table, and then also some directing sheet metal using clamps. So, in this case, the sheet metal is pretty easily removable. That foam can be a real challenge. Anybody have foam issues on equipment in terms of cleaning? Thank you. Yeah. talking a little bit about buildings as well. Coving is a really nice practice for areas that see a lot of water, or where you're either in your washing process there's a lot of water, or in your cleaning and sanitizing. So having coving and drains. This is another example of sinks and tables that have an open edge on the outer perimeter. Sometimes they're rolled back on themselves and crimped, and that can become a collection point. The fourth area of hygienic design to consider is compatible materials. And so we've talked a bit about this already, and there is a lot of good work happening. And I've been encouraged by the conversations I've had with manufacturers around this topic. They are interested in doing things better and making sure that you all are receiving equipment that is more easy to clean. This is an example of a root washer that was 100% carbon steel, and you can see what happens over time is there's staining, there's rusting, and the paint is peeling. A lot of the farms we work with are quite small scale, and so there's a variety of sinks and tanks used. Again, the key being, are the materials smooth, cleanable, compatible for not only the use in cleaning the fruit and vegetables, but also in using detergents and sanitizers. This is a stainless steel version of the root washer we were just talking about. One of the key things I like about this is, again, it's got an access area right here for getting inside for cleaning. And then the fifth key point of hygienic design is preventing contamination. So this is thinking about more broadly around the specific piece of equipment and looking at the building and thinking about how we prevent contamination getting onto the produce that we've worked so hard to protect getting to this point. So that might be like excluding birds and rodents, et cetera, but also thinking about where do we walk and where do our harvest bins go and things like that. And just a reminder from Produce Safety Alliance, lots of potential contamination sources, so thinking about how all these things either can or can't get into the specific piece of equipment or the building. I'm going to skip a little bit of this just because of time. I apologize. But one thing is, I don't know how much people have focused on issues related to birds for bird exclusion, but some pretty simple solutions in terms of netting for more outdoor pack houses and things like that, netting under rafters. This is nylon. Yep. Condensation, I know we get plenty of condensation on cold water pipes, so thinking about how to direct that somewhere away from where produce is being handled, and just some simple gutter solutions here. So again, the purpose of hygienic design is to intentionally create or improve spaces and equipment so they can be cleaned and sanitized. We know why we're doing this. These are the 5 key principles. These are the materials I was referring to. There's a guide sheet that covers all of this in a PDF form, and then there's a checklist that covers it section by section. And the point of this checklist is to sit down or walk around a piece of equipment with your team and do a self-assessment. And it gives you prompts for each section. So, are all food contact surfaces visible and reachable without significant effort or tools? If that's the case, you give yourself a rating somewhere between 7 and 10 on that item. If it's not, you go to the next one. They're not visible and reachable, but they can be made so with ease. For example, we have a tool attached to the machine that gives us access. Then you get a 3 to 6 for that item. So it's a way of going through and for that point in time, giving yourself a score. And then also thinking about on the right-hand side, what would we do to improve our ability here? So it's a way of assessing and making a bit of a plan. And the idea is you do this, you make some improvements, and you come back and see how it's been going. And that gets to the last point here. There's a lot of perfect being presented. And remember that it's about the steps towards better, right? So trying to maintain a continuous improvement mindset. That's why, although there's a rating here, it's not meant to rate you against other people. It's meant for you to have a snapshot in time and to work towards improvement. All right, I hope that was helpful. I appreciate the participation and the contributions. Thanks, everybody.
All right. Thank you, Chris. We really appreciate your presentation. Are there any questions really quick from the audience? Okay. Not seeing any hands. Thank you again. And now we will move to Faith Kreitzer, who is going to talk about sanitizing harvest bins and picker bags, a validation study. Faith is with the University of Georgia.
Thank you all. We're going to show a little bit more data. I know a lot of these talks are general in scope, so hopefully I don't put you to sleep, and hopefully I do a good job of explaining it so that you can get some takeaways from it. Okay, great. This study was funded by the Center for Produce Safety and was supported through the Specialty Crop Block Grant Program. So just as with many things, know that these are just my opinions and conclusions. They do not support, or not supported by any federal authority or anything along those lines. In this project, we were actually looking at something specific to tree fruit, because I was at Washington State at the time. But we see a lot of these same surfaces used in produce. And to Chris's point, we know that there are challenges that come with them. So we're going to today focus specifically on wood, hard plastic, and nylon. And nylon, that's a fabric, Cordura is the brand name, that we commonly see in some of our picking bags and things along those lines for commodities that we pick into. This work was done by a group primarily led by Valentina Trinetta from Kansas State University and other people within her team and myself here at the University of Georgia. And then here are the people who did the real work, who are going out and doing the in-lab studies that we'll talk about today, as well as the on-site field trials. They were part of Dr. Trinetta's and my team, so I definitely want to give them some face time for their hard work. So ultimately, what we were trying to do is actually go in and collect data. And when we do studies like this, our goal is we can give you now data that you can show and use along with other things if you are getting pushback, right, on the effectiveness of your sanitation programs with some of these less ideal surfaces, and really help improve them. So in that regard, what we did was we actually inoculated with, our leading foodborne pathogens. So the ones we're going to talk about today are Listeria and Salmonella and Shiga toxigenic E. coli. These are all bacteria. They tend to be our leading, as far as bacteria go, the ones we are most concerned with fresh produce, the ones we see the most outbreaks associated with. And we wanted to see how well different sanitation approaches worked when we were looking at different food contact surfaces. And we were really focusing on the sanitizers within this study. So know that. So here's some of these materials in place. So here we have our picking bags. Right here, that's going to be our nylon. So you'll see that represented as nylon. And then we have our hard plastic bins as well as our wood bins. And I would say, coming from Washington State, while we know that wood bins are porous and they're really hard to clean, they're also far easier to replace from a cost perspective, and they're far more easily handled when it comes to slippage and breakage and things along those lines. So they acknowledge that and they identify with it, and they are looking at things like, bin liners and stuff like that. But even with that, typically the bottoms are open because those apples are going into storage, and you may have decay occurring during that time. So you don't want them fully enclosed because that will actually promote further decay. So the actual sanitizers that we looked at are what I'd say two of our tried and true, right? So we're looking at chlorine, right? So that could be, in this case, it was sodium hypochlorite, which is like liquid bleach, right? But you also have forms like calcium hypochlorite that you can work from in powder form. We also had peroxyacetic acid, or PAA, a lot of times is what that's abbreviated to. And we tried both of those at 500 parts per million. We worked with the suppliers of those products that we were using. It was within the labeled ranges for food contact surfaces. And just know that not every PAA or chlorine product may have labels that go up that high. If you want to talk more with me about that after, we can. We also looked at two that are more emerging, or say are newer, especially within the produce industry. Silver dihydrogen citrate, or SDC, is a product that a lot of people had interest in, weren't really sure, about if its efficacy or if it was worth looking at. And essentially, this was in a 4% suspended solution. The one nice part about this is it was ready to use. So there was no mixing to it at all. It was ready to use, and that was a benefit, especially if you're going back and doing re-sanitation or like sanitizing again on a spot or something for need. We also looked at chlorine dioxide, and that was applied as a gas. It was not suspended in liquid. There are different formats where you can actually get it in water and other things, but we were applying it as a gas. The idea was, for larger operations, which is what we focused on in Washington State, you could fill a whole CA room, right? And then gas your bins at the end of the season before you go out and use them for next year. In smaller operations, you tint them, and essentially you can achieve the same thing if you don't have an enclosed facility. We also looked at steam, and steam falls outside. It's a device, right? So it falls outside of our sanitizer, and a lot of times with the devices, they don't come with as much documentation. The suppliers cannot sell you something that does not do the job they say it does, but at the same time, they may not be looking at your surfaces or even aligned with your industry at all. So there may not be as much support there as you get with your labeled chemistries that you have for sanitizers. And we tried that for 75 PSI with steam generation. And we picked our generator based upon what was being marketed to the industries that we were working with at that time. So it's not to say that there aren't bigger units out there, but this was something that was like more backpack style, handheld, could be more easily potable than some of the larger units we get with higher temperatures. We're also going to look at, again, two forms of these bacterial lives, and I put green circles around them. So we looked at what we called sessile cells, and these are just like the microorganisms that are going to fall on a surface. And our goal is to always inactivate at this point in time, because they're far easier to control and get rid of. Versus once they start growing in these biofilms, because you have nooks and crannies that you can access, and there's opportunity because there's always a lot of nutrients around, they will grow. And at some point, we can even start to visually see this happening, right? It'll be a film that's forming. I know in my dog bowls at home, I always have to work hard to keep the biofilms from building in there, but it just happens over time naturally if you aren't sanitizing those and cleaning those frequently enough. So we looked at both of those in this work. Know that we also, to grow these biofilms, we did it in a very controlled way just because it's research, right? And it has to be reproducible. So we take these biofilm reactors, we put those surfaces on small coupons, and we essentially grow these microorganisms on them so that we know that they're there in a biofilm. Would this be what would happen in your packing house? By all means, no, right? But this is the way that the EPA moves forward with looking at things that are biofilm related for either medical devices or for food manufacturing, any number of uses. So let's get into some of our results to get started with. I'm going to try and not kill you with a bunch of slides and a bunch of bars, but just to orient you a little bit, we have all of our treatments right down here. So we have our controls always going to be first, silver dihydrogen citrate for 1 or 2 minutes, chlorine for 1 or 2 minutes, PAA for 1 or 2 minutes. We also looked at steam. We cut the steam time to just half a minute and a minute. Does anybody know why we had to cut the steam time down? Nobody's going to sit there at a surface for 30 seconds and treat with steam, right? Even that seemed a little bit outrageous. So we went down a bit, and we were able to hit the targeted 140 temperature, right, which is what we commonly refer to. Honestly, the best guidelines you can find are probably for restaurants and what they're trying to use when they use heat for inactivation. We were able to achieve that. Know that if we were doing something like a bristle brush or something like that with steam, it melts those even within 30 seconds. So know that they're not fit for every single plastic out there. We also had chlorine dioxide here on the very end. You'll notice it just has one time period because with chlorine dioxide, it's harmful for us to inhale it. So we actually have to have basically that tinning in place. We cannot be breathing in it. It's dangerous to us. So you come back after 24 hours and essentially remove it from those containers. And that's enough time for it to dissipate. Within this treatment, these are for specifically Listeria monocytogenes, so I'll always put the organism up here, and then what form. So we're going to go through the sessile ones first. These should have been our easiest ones to inactivate. Green is nylon, so that's our picking bags. Orange right here is wood, and then the blue ones are plastic. So again, y'all are getting your junior microbiology badges today. We have these populations in log units. Know that if it has a 1, that just means the number of zeros after it, right? So if it's 1, that means 10. If there's a 2 here, that means 100. 3, that means 1,000. So it's an order of magnitude, so we can show you really high populations all in the same graph with really small populations. And no, we inoculated at really high levels for these. If any of the treatments along here fell within this bar, they gave us at least a 99% reduction. That aligns to a 2-log inactivation from those controls, but it's a way that many times we talk about, with sanitizers. I know that after the pandemic, and you all are in food safety, so you're used to looking at this anyways, this is far easier to understand. So as we go down each log, we will see more inactivation. Our goal is to get at least a 3-log inactivation and to a 5-log inactivation, depending if it's a food contact surface versus not. Here's our 99.9% reduction. Here's our 99.99% reduction, which is a 4-log inactivation, where we had the best performance overall. You can tell that came from our silver dihydrogen citrate at the longest time period, as well as our chlorine and PAA. One thing that I was really surprised about within this study is that, we got the greatest inactivation on plastic. That was not anything I was that surprised by, because it's non-porous, right? It's far easier. But the greater time did not impact efficacy, right? So we didn't really see that benefit within here. And we were able to identify treatments that result in at least a 2-log inactivation above that of a water-only control for all of our food contact surfaces. So know that that was good, but definitely we did not see as much efficacy out of steam, and we did not see quite as much efficacy out of nylon picking bags for whatever reason on Listeria and our chlorine dioxide treatment. I'm going to keep on moving through these. This is E. coli, right? So the same exact setup that we saw before, and we're looking at these again with our sessile cells. So here's our 99.9. You can see that many times this is where our nylon's coming up to, like we're good if we can get inactivation there with E. coli. As we change between these organisms, they have different innate defenses to them, so they don't all perform exactly the same. Here we have our 99.9% reduction here, a bar coming across. And then we have our 99.99% reduction. And then we actually saw a little bit more activity here with our Shiga toxigenic E. coli amongst some treatments. Notice that sometimes the chlorine dioxide did work relatively well, but it wasn't across the board for all the organisms that we were testing on all surfaces. So some of the consistent trends that we saw when we compare this to what we just talked about with Listeria was that we still saw the best performance on plastic. So I think that that goes a long way. A lot of times if you're in the food safety role, just being able to justify why it's worth investing in something may be really important, right, for you. So please utilize stuff like this to say, this isn't just us spending money for the sake of spending money. It's going to give us a more cleanable surface if you are using something that's more porous. Again, that greater time did not significantly alter efficacy, but we did see better inactivation in general when we compared it to Listeria versus the Shiga toxigenic E. coli, which is the type of E. coli that makes us sick in foods most commonly. Again, we still saw treatments that at least gave us that 2-log inactivation, even on these harder to sanitize surfaces above that of our water-only control. And know that our water-only control was working. It was removing things just by physical force, right? But it wasn't actually inactivating. It was just kind of redepositing it to wherever that water went. Now we have salmonella lastly, and then I'll talk about some of our biofilm data. Here's our 99% reduction, our 3-log inactivation, 99.9, 99.99, and up to our 5-log inactivation, which is our goal many times. So ultimately, our consistent trends are we saw our best performance on plastic, we did not see that time benefit, and we saw that greater than 2-log inactivation. And we didn't see as much of a split between Listeria, and it definitely aligned much more with E. coli versus Listeria. So I would say it's important to know if you have history, and I think most of the produce world does have history with Listeria, it is going to be a little bit harder to inactivate with these sanitizers in general. So ultimately for our sessile forms, which is what we're trying to target, this is probably going to be our best shot for inactivating these things. The material is going to impact a lot, right? So we're not going to see uniform efficacy. I have some really nice pictures coming up that maybe explain a little bit more why nylon's so challenging. But that was unexpected from us. We knew it was a weave, but we didn't know it would behave similar to that porous surface. When comparing chlorine and PA had better efficacy than chlorine more frequently when you compared it across all the different treatment combinations for organisms and surfaces. That handheld steam treatment did not seem feasible. Ultimately, is even just doing it in the lab for research purposes, like this is not going to work long term. And especially when you go out and observe the industry, the way that they're using it, they're using it as, at most for cleaning, I would say is where I would put it, my stock in steam. If you actually tinted to contain steam, I can tell you the deli slicer industry that's mechanized, they steam their equipment a lot on a less regular basis. They trap that steam. They literally cook that equipment, and the equipment's designed to be done in that manner. So know that this is us doing it in open air without those caveats. Now I'm going to move into the biofilms, and we'll go through this. So it's all the same setup that we just talked about before. Here's our bars coming in for our different inactivations, and we saw very similar trends, and we actually got pretty good inactivation with the biofilms. The caveat I will say for this data is that those biofilms are on small coupons, and they are more easily dislodged at the end of the day. So when we went back and tested those coupons, they were you're able to actually chunk it off, if that's easy to conceptualize. So you actually don't recover it on the surface. It wasn't as tightly bound. That may be a function of the way that specific biofilm's growing within that reactor, though, at the end of the day. So we saw our best performance on spray-based applications. That aligns to you're actually physically removing that on some levels. Less reduction for biofilm on wood and nylon compared to our sessile when we looked at those. We did see that chlorine dioxide performed much better when the organisms were in a biofilm. Historically, in other facets of food manufacturing, we use chlorine dioxide on an irregular basis to get rid of biofilms in like cooling tunnels and other areas that are really hard to reach because it is a gas, it will go everywhere, and as long as you can protect the people, right, when you're treating with it, it is really good at removing that. So we knew that was a benefit of chlorine dioxide coming in to begin with. Here's again, moving from Salmonella to E. coli, very similar trends here across the board. Oh, sorry, one too many. Again, we saw better performance on our spray applications for our sanitizers. Greater time did not really impact efficacy with the controls that we used. And we saw that chlorine dioxide still holding true and working really well as we moved from one organism to the other. And then we saw, again, we had some treatments that showed really great activity overall. Here's our last one. I'm going to stop boring you with this data, but here's our Salmonella data coming in. We actually saw the best inactivation with Salmonella in general when we looked at them across the board. Maybe this one, I have one more. But again, very similar trends. The biggest difference here when you compare it to the other work that I showed with the sessile forms is really how well that chlorine dioxide treatment did work across the board for these biofilms. So if you're ever kind of struggling with how you're going to deal with something, know that that may be a real special sort of application for you to use for special time periods. It's not going to be an everyday sort of sanitation approach. But for special causes, that may be a really great solution. I don't know that we've looked at in that great a detail for fresh produce. We also see that this is some of the pictures I was talking about. So when we looked at nylon, the way that so I like the picture up here at the top, right? You can see those weave coming in. You can see how, yeah, it's kind of like, it's not a porous surface, but it kind of is because it's multi-layers on top of each other. And once inoculated, things get trapped in there, and then they're kind of inaccessible even when we're putting them in sanitizers and really exposing them to high concentrations of sanitizers across the board. On this bottom, what we have here is what the topography, when we are growing these biofilms in this reactor, well, you can actually go in, they basically take a needle and they scratch it over so you can get kind of this topography map. And it's just like any other topography map. The greater it is where you're actually seeing those microorganisms grow and that biofilm increase. So you can see here, they kind of just align. This is the basic weave, right? So you don't have a lot of growth happening here. This is what the surface would look like to begin with. But what do you notice after you give it 24 hours? It's some of those valleys that were once there have now filled in, right? So that's your biofilm growing, and then you see it even more, and it's not all across the surface, right? It's in very localized areas where you can actually see this biofilm coming in and filling in those gaps. So I think that goes a long way to explaining why nylon was the challenge it was and aligned much closer to wood than we would have thought initially. Here's the same thing on wood. So again, here's wood, right? So a lot of surfaces there. It's a natural surface, so they're going to be arranged. There is some order there, but it's not quite like a manufactured surface. And here's what it looked like starting out. So this is kind of our base level, right? And then you can tell we get more and more build-in as those microorganisms grow. They produce all those exopolysaccharides, which is like the film ultimately that you experience when you're trying to clean biofilms. And look at how well they're filled in after those 96 hours in that reactor. These are worst case scenarios. We are feeding these things, but no, if you give something longer periods of time, like you would in a packing season, you still get to that same place, even if they're not getting the same amount of nutrients, right? It will still occur over time, unless it's a really dry area, right? But as long as there's moisture and as long as there's nutrients, you're going to have these issues. Here's what plastic looks like. You can tell plastic is nice because it's fairly flat, right? And that's the nice thing about it. But as you start to see these, essentially what you're seeing is the microbial growth as it pops up at 24 hours. And then again, here at 96, you can see there's even more of it. So ultimately, we had, most of our treatments showed some sort of activity. Out of the 180 we tested, all these different treatment combinations, we saw that. In all situations, at least one of the most commonly used sanitizers, being PAA or chlorine, did result in really good inactivation on these various surfaces. And so I would say that this data, we're publishing it now, right? So it'll be out there and it's open access. So if you want any information on it, feel free to follow up with me at the end of this session. I'll be happy to pass that along to you. Know that, if anything, you can prevent the formation of biofilms by the frequency of your sanitation events. That's really our only strategy for that. Nylon and wood are going to be difficult, but we did see different microbial accumulation on different materials that really helped us kind of explain some of the way that these microorganisms layer on and why they're so hard. We actually took this to field trials with small to medium-sized growers in the Midwest and larger grower packers in Washington State because we're focusing on tree fruit. We decided to go with the oddballs because that's what our industry partners told us they wanted us to look at. That they're like, yeah, we do chlorine and PA, stop it. Why don't you look at some of these other things that you were testing out? So we looked at silver dihydrogen citrate, and the trade name of the product was Pure. We also looked at chlorine dioxide gas for 24 hours. So let's look at some of that data. These were our field sites, and we really appreciate those partners who let us come in and derail some of their time for a few days. What we did is, because we needed to inoculate these coupons and we were using real systems, I would say the biggest thing when you're loading with something like chlorine dioxide, any organic matter also takes away some of the activity. So we really wanted use materials in there, but we actually inoculated these things and just put them on the side because we needed to take them back off and be able to count the microorganisms on there. You can see the wood bins. This was a 98 bin. I asked them for the oldest that still met that means that it graduated high school at the same time. I graduated high school in 97. That's old, I can tell you. So here we are with a bin that's still being used. It's wood, and we have our plastic bins here that we're using, and these are some of the examples of the picking bags. And these are still they're using them, right? So this wasn't special. For our biofilms, what we did is we left them basically to grow. And for our sessile forms, I had to go out from Georgia to Washington, so we had a little bit of time with the sessile. They may be more like a biofilm, honestly. There's the starting stages of biofilm when we got there, but we essentially tested in these two forms. Here's what chlorine dioxide application looked like on the smaller scale. Again, once you scale this up, You'll need fans and other things, but you can scale it up quite large. But we tinted in this case, and this is our meter coming out so we can measure how much chlorine dioxide curve we got. Here's what we were doing for the picking bags. You can put them in any impervious container, and we can get treatment there. So what did these results look like? For our Midwest regions, they actually don't use wood, and there was a smaller facility, right? So they were using smaller plastic and nylon picking bags. What we saw here is that the silver dihydrogen citrate really did not give us much bang for our buck when we used it. Even though it would be nice to have a ready-to-use surface, it did not. It did give us significant inactivation, but it wasn't as great as we had seen in the lab. We also see that chlorine dioxide in the Midwest region works really well in this instance. This is Listeria inocua, which is one of our non-pathogenic surrogates we use to model Listeria. So that's what this inactivation was for, but you can see that that chlorine dioxide treatment was really effective. This is data, same organism, but in Washington State where they did have wood, so that's why you have a little bit more complexity there in 3 bars. You'll notice, as great as chlorine dioxide worked in the Midwest, it did not work as well for us in Washington State. Since y'all probably have never been there, you're in an inland desert, and something that makes chlorine dioxide far more effective is humidity. And in this environment, we had far less humidity. So it would help if you wanted this as a strategy to actually boost humidity. So that is finally in the Southeast, there's a good reason to have humidity, right? So we're sitting pretty right now compared to what we saw. But that's what we attributed the difference in these different profiles. You can tell wood here was on the end. It still did not do a great job on wood. We may have seen slightly more inactivation if we were in a slightly more humid environment, potentially. Didn't really work well, though. Here's the same data looking at E. coli. This is just generic E. coli. So again, very similar trends to what we saw with Listeria. This is the Midwest data with really great observations occurring with chlorine dioxide. This is our Washington data, and it also held very true with this generic E. coli and what we saw for Listeria. With the chlorine dioxide, we got inactivation, but it just wasn't as great compared to what we saw in the Midwest, given that humidity difference. So in bringing it all home, definitely the sanitizer, go figure the surface, and the combination of those 2 factors were all important. There's a difference in microbial reduction observed for the same treatment depending upon the location for these field sites. Specifically chlorine dioxide, we're going to want to control humidity and get that as high as possible when we're treating with chlorine dioxide gas. Know that RA rooms, if you're looking at this for that specific, it should be boosted to greater than 90%, and they have that capacity. That's normally what they do when they're holding product in it. Another thing we observed that was unexpected, because at the lab, you're kind of controlling everything because they may have pathogens in them. This is silver dihydrogen citrate residue after we applied it. I don't think your sanitation crew is going to, or the person coming in and verifying your sanitation was effective is going to be very happy with having this white powder all over the place. It also forms on stainless steel. I talked to a lot of the industry partners who were kind of testing it out for certain purposes. They're like, yep, this is very common. We see this a lot. It'll at least form a film or a residue on it. Sometimes we get that with quaternary ammonia compounds, but this is it was like a chalky, and it wasn't actually on the bins. Like you can see the inside of the bin that was sprayed with it. It was just where it sat for longer periods of time on the floor. I think that would be an issue though. So bringing it all home and combining those 2 together, prevention of biofilms, I would say, is really key. So get your sanitation, your master sanitation programs in place to try and prevent that from occurring. Know that what we're using, even on porous surfaces, we are getting some inactivation. So I would say don't think, oh, it's not worth doing because it's harder, right? Know that chlorine dioxide may be an alternative that we can look at for some special use causes like we do in other segments of the food industry. And in those field trials, humidity played a big role. And we didn't alter humidity because we were trying to go with what the industry best wanted to try and approach. But I would say controlling that humidity is going to be key if you ever want to look at that. So thank you again to our funding sources and all the great people who partnered with us. And I think maybe I have a minute or so, maybe, for a question or two if anybody has anything.
Does anyone have a question?
Yeah. So if a grower's currently using wood bins, I'm a big fan of the bin liners, unless I know that hurts sustainability purposes, right? But I think the bin liners for commodity that's moving really quickly through, they're a barrier, right? So that is one mitigation strategy. If you're not going to go that direction, I would say sanitize, right? And get, for things that may have decay or residue in it, actually get them clean, right? So many people are just trying to sanitize and they weren't cleaning up front. So it's really important, even though it may not be as ideal a surface, you still are going to see benefits and reductions, which equate to mitigating that risk if you try that approach. And I would try and get the highest labeled rate you can apply for that sanitizer that you're using. So shop around at your labels, because not all are going to have 500 parts per million. And some may start to try and push higher. In the meat industry, they go far higher than this. So know that there's other sanitizers out there that you may be able to use. And I would try to go with the highest rate possible for a porous surface. Yeah.
Are there farms that you're aware of that are using the chlorine dioxide, the gas, and what does that system look like for say a medium-sized grower?
Yeah, it's actually really applicable to any size grower, because all you do is mix two reagents together in the system that we used. And I can give you more specifics on that. But you can scale that down or scale that up. The biggest thing was once you honestly start scaling up, because you need to then start moving that gas around and getting that. Did you want to say something, Natalie?
I was just going to say, as someone who has used chlorine dioxide in really large processing facilities, because it is so good at because it is so good at penetrating and getting rid of biofilms, it's really, really, really important to do a full sanitation afterwards to get rid of the rest of everything else. And if you do that, it can be really effective, because when we would do that as a knockdown once a year, our environmental monitoring program, we would see no activity for months. So it's really effective in the right environment, but you do need to make sure you do the steps in the process. And we used a dual, it was a foam followed by a gas process.
Thank you. All right.
Wonderful. Thank you all. Thanks for the questions.
Thank you, Faith. We really appreciate your presentation. Next up, we have a presentation titled HACCP Post-Harvest Water Management and Corrective Actions. This presentation was put together by Alexis Hamilton with Virginia Tech, but will be presented by Laurel Dunn of UGA due to weather.
All right. Well, I am obviously, as she said, not Alexis Hamilton, and I'm sorry you're deprived of hearing her, because I know she had this presentation prepared and down for you and was really excited about it. But we're going to discuss a bit about how in a post-harvest system we can use a HACCP-based approach to make sure that we're managing some of our food safety hazards and also keeping up with some of our audit and regulatory requirements for our really everything post-harvest. So we're going to go through a few slides. Some of these are going to look familiar for those of you who have been through the Produce Safety Alliance grower training. For those of you that have not, or that might need a little refresher, I just want to make sure you are aware of what I mean by post-harvest water and why we are concerned with it and why we need to have some strategies in place in order to manage some of these food safety hazards. So when I'm saying post-harvest water, from a produce safety rule standpoint, what we're meaning is anything that touches that harvestable portion of the crop, either during harvest or sometime after harvest. So we'll see this in our operations when we're rinsing or washing produce, if we're flaming that produce, cooling it, using ice on it for cooling. Also our hand washing and some of our cleaning and sanitizing comes in this. What we're really focusing on for the context of this talk is this rinsing and this washing, or our commodity movement applications where we have large volumes of water that we're putting a lot of produce into. Why we're interested in this is because we know we can have everything perfectly right in the production environment, and we can still be bringing in foodborne pathogens on our produce via our employees, dirt, fecal material that might make its way in, soil, other things like that. And so we need to have these robust post-harvest interventions in place to make sure, particularly for these situations, where we have batch water, we're putting a lot of produce in at once. If we have even a small amount of contamination that's entering on this produce, we put it in a big bucket or, thousands of gallons of water or tens of thousands of gallons of water, that contamination is going to spread from that small amount of contaminated produce really to every other piece of produce that comes into the system, because as it's going to disperse, those microorganisms might come off of one or two commodities, one or two pieces of produce. They're going to be in the water. Without a sanitizer in that water in order to kill anything entering the water, we can get a lot of contamination going on to a large amount of produce. So we really need to be staying on top of our post-harvest sanitizer if we're using it in our system. Now, back to produce safety rule, we obviously don't have to use a sanitizer, but a lot of our audits, a lot of our buyers are going to be requiring that sanitizer usage. So for our post-harvest water, we have to know that initial quality of our water. For post-harvest water, how much generic E. coli can we have in that water that we're using? I'm seeing heads, so I'm going to assume that is our answering for our zero detectable generic E. coli when we start using that water, and we need to make sure we're maintaining that level throughout the entire production of that. So our best way to make sure that if we're using large volumes of water that we aren't getting E. coli building up in that, and when we say E. coli, we're really worried about our other pathogens building up in that water, or our Shiga toxigenic E. coli building up in it. Our best tool that we have are using these sanitizers. So chlorine, peroxyacetic acid are most commonly used in our production water. Again, not washing the produce. These sanitizers aren't typically effective in removing attached contamination. So if you have produce going in that's already contaminated, you might not be able to remove it unless you cook it off, but we're really trying to prevent that cross-contamination to our clean produce that might also be in that system. So all about risk reduction in the system, and that's why we're going to get into our HACCP-based approach in just a second. And as Faith kind of already mentioned in hers, again, we're using these that are going to be labeled for those appropriate usages and at the appropriate levels. And we've all been discussing, I'm not going to dive into this too much, but cross-contamination from that produce is what we're really concerned about. And with this water usage, really we're focused on this direct contact with our covered produce for the next few slides. That's what we're really focusing on. So when we're doing this, we're using water that is either treated or is groundwater or is municipal water that we know has zero detectable generic E. coli for starting out. All right. So what happens if you are processing and you realize that your water does not meet the water quality criteria that we just discussed? So what are we supposed to do in a situation where we are washing and we suddenly realize that there's the likelihood to have that E. coli in our water? How do we approach that? How do we make sure that we are protecting our consumers and still selling a safe product? So if you don't meet that water quality criteria, what you are is a situation where you can no longer reasonably guarantee the safety of your product. You're going to need to implement some sort of corrective action and take control of your product again and take control of your process again. So we really like implementing a HACCP-based approach for these scenarios. So how many of us are familiar with HACCP in the room? Okay, oh wow, all right. Well, then I'm not going to spend too much time going into this, but for those of you who didn't raise your hands, you might be less familiar with this. When I say HACCP, that is our acronym for Hazard Analysis Critical Control Points. In order to determine whether or not we have a safe food product, the way we can ensure that we have a 100% safe food product that's not going to make anyone safe is by testing every bit of that food product. Problem with that being, we test every piece of that product. We have destructive processes to do this. We now have nothing to sell. If we do absolutely no product testing, we really have no sense of the safety of our product. But we have those limitations of just not knowing what's in that system. You can fall somewhere in the middle here. but you can also implement a HACCP-based approach, and I think we're going to see that slide again and see where that falls into that. So with HACCP, those of you who might be familiar, or those of you who aren't, I guess, HACCP began as a partnership among Pillsbury, the Army, and NASA with this goal of, all right, we're back to this slide where we need to send astronauts with safe food. The only 100% way we know that food is safe is by testing it, and then we destroy all of our product as soon as we test it. So how do we make sure that these astronauts that we're going to put in a very tiny space shuttle for extended periods of time with very sensitive equipment that we don't need impacted by liquid that might be coming out of a sick astronaut with either direction from them, we need to come up with a system that makes sure that we're sending these people with really safe food, that they're not going to get a foodborne illness when they have zero gravity and are crammed in a space shuttle. So this approach really kind of fell into take that space between, all right, we can't necessarily test. How do we make sure that every time we make a product, we're making that as safely as we can, and we're controlling every step of the process where foodborne hazards might be introduced? And that was really where HACCP came about, and it kind of started or had its birth in the 1960s and has really just kind of exploded to where it is an internationally recognized and accepted program now, really geared more towards food manufacturing, but we're using it much more in the produce industry now. Just as your bonus question that Alexis put into this, does anyone know what the first food in space was? Anyone? Anyone? I'll give you a pat on the head or something if you get this. What was that? Oh, I heard Jell-O, but close actually, because I also heard the right answer on the front row, Tang. So if anyone's had a hankering for an orange beverage lately, next time you reach for some Tang, you can think about how that was our first food that went up into space. So where we have HACCP now is kind of falling into this area where we're not relying so much on testing to determine whether or not our product is likely safe. And so we're still never going to say 100% safe with something like HACCP. But with a HACCP program, if we know our process is safe and we can prove that we're following that process, it's very likely that our food product is safe. We are anticipating the hazards coming in. We have controls in place or processes in place to make sure that we're controlling those potential hazards. And so in most scenarios, the food we're putting out, barring any extreme situations or things that we might have overlooked, we're making a safe or a likely safe food product. So HACCP is where we are really testing that process we have in place. And I promise I'm going to get to post-harvest production water here in a second. So when we're saying this HACCP approach, we're systematically anticipating and controlling our potential food safety hazards. So we'll break this down briefly. Systematically, we're following a step-by-step process. Every time we make a food, or in this case, every time we wash our produce, we have step-by-step procedures that we're following, and it's done every single time. We are anticipating. So HACCP requires setup on the front end. A HACCP plan doesn't accidentally happen. A HACCP plan is where you go through your facility, you go through your washing system, and you figure out, all right, where could my issues come in? What hazards are inherent to the product I'm making? So in fresh produce, we probably have contamination coming in on some of our produce that we don't want spreading to our others. So that would be some of our risks, our hazards. Our equipment, depending if we're using some of that legacy equipment that Faith and Chris were talking about earlier, that might be a way to introduce hazards. So we need to anticipate where some of those can come in. Control. We love these three things in HACCP. You're either preventing, eliminating, or reducing to a publicly safe level some sort of hazard. So you're preventing it from happening in the first place, or you're reducing it or eliminating it completely. We're interested in these potential problems, even if you've never had that problem in the past. So we tend to get talking to people about food safety, and we hear the line people really like of, well, I've never made anyone sick, or that's not a problem we've ever had. All right, if it's something that has happened on another farm or another operation, or is likely when you're conducting this hazard analysis to happen in your operation, if there is the potential for it, even if it's never happened to you, you need to be addressing it in your food safety programming in your HACCP plan. And so when we're saying food safety hazards, we're discussing our biological, our chemical, and our physical agents. In this context, I'm really focusing on these biological agents, our Salmonella, or E. coli, or Listeria, our primary foodborne pathogens that are going to cause a consumer harm or illness after they consume it. So how do I take this HACCP approach? You're going through and determining what can contaminate my product. How would I know if it contaminated my product? A lot of times, we don't know. If we knew our product was contaminated, we wouldn't have sold it in the first place. So all these recalls, most of the time, people would not have put it in the marketplace if they thought it was contaminated. So how am I going to know if mine is contaminated? What do I have in place to determine that my product might not be safe? How do I prevent that from reaching a consumer? Because the last thing I want to do is to make people sick. And then how do I prove that I prevented that contamination from entering the marketplace? How am I making sure that if someone realizes, like, oh, on this day your system wasn't working, what paperwork do I have to show, yeah, my system failed, but we made sure the product never made it to harm any consumers? So we're going to get into a little situation here where we find that our sanitizer concentration is outside the critical limit. So we have decided that we have a certain amount of our sanitizer that we need to use in water, and in this scenario, we don't have enough. So we work for a company that packs out fresh produce after a short wash in a dump tank. The company has been working to reduce its water use, so it's switched to recirculating the water use in the dump tank. They minimize cross-contamination risks by using peroxyacetic acid to the dump tank water. So they're using PAA in their dump tank water. You are responsible for checking the concentration in the dump tank at startup, mid-shift, and at the end of the day to make sure there's enough in order to reduce that microbial population in the water. When you check the dump tank at mid-shift, you cannot detect any sanitizer. So you have no idea if you are controlling your microbial hazards in the water. You are no longer sure if you are making a safe product or if you have been potentially washing clean produce with dirty produce and your product might not be any safe. So what do you do in this situation? We're going to go through how you would address this and how you would handle this in order to make sure your consumers aren't getting sick. So as we kind of discussed, we have our biological, chemical, and physical hazards. Here, we're worried about that microbiological hazard. Our level's too low, so we're not worried about a chemical hazard. We don't have too much PAA. That would be another issue. We're worried about our biological hazard here. So how would we know if it contaminated my product? Well, in this case, we know we might have a microbiological hazard that has contaminated our product because we have been actively monitoring our system. We went midday, we tested our water, we realized due to our monitoring, our system was out of control, and we were not monitoring that, or we were not adding enough sanitizer to that water. So in this case, it was our sanitizer concentration. So the operation is monitoring how much PAA, and since it fell below that minimum amount, they can no longer be sure they're protecting that food and ensuring the safety of that food. They're also going to have some validation data that's showing that their control strategy works. So in this case, for something like a peroxyacetic acid, your validation data is your EPA label saying what concentration that you need to be using in that system. So they have it validated because they're using a validated sanitizer that is approved for that usage, and they're using it at the appropriate concentration and on the appropriate product. So keeping in mind, if you're doing this, they're using a PAA that is labeled for direct use on fruits and vegetables. All right, so how do I prevent that contaminated product from reaching my buyers or consumers? This is where we start getting into part one of our corrective action. So the first thing the operation did was they immediately added more PAA to the dump tank until they reached the target concentration. So they brought their system back under control in order to make sure that they weren't continuing to wash any produce. They also immediately figured out what product had been affected. Now, the problem for them in this situation is since they knew the sanitizer was at the right concentration at the beginning of the day, but they had no idea when it dropped off between the beginning and midday when they measured, they don't know when they lost control of the situation. So they're going to have to go back to when they knew they had control of that system and really go back and isolate everything from when they knew it was under their control to when they lost it. So they're looking at losing about a half day of production here, but they're isolating the product. And then they have to determine what they're going to do with this product. So in a situation like this, they have a few options, or they might decide, depending on how much was washed and what was washed, just to destroy the product. They might determine that, well, maybe we can divert this product to an instance where it might be cooked. So we know we have a microbiological hazard here. We know that this is something that, if we were processing tomatoes in this instance, maybe these are now going to be our canned tomatoes or tomato sauce, something that's going to get a thermal process in order to control that microbiological hazard. I really like this donate to science. Give it to one of us poor researchers who's scrambling to find stuff to sample, or who needs it for some other purpose. Make sure you are not donating it to your food bank, please, or to anyone else who might be eating it, because we don't know if this is safe, but it could be potentially to someone who might be using it for some other purpose. Yes? In this situation, this would have been a CCP, a critical control point. Yes. So then the next thing they're going to need to do is to take steps to prevent this from happening again. So with our corrective actions, this is usually a two-step process. So you kind of have that initial where, all right, I'm going to fix it immediately and figure out how I'm not getting product into the market. And then you have that secondary step that's like, all right, how do I make sure this didn't happen again? What am I going to do for that long-term fix? So then, how do I prove that I prevented that contaminated product from reaching my buyers or consumers? So how do I make sure, or how do I prove that if someone comes along later and sees my records, they're like, hey, you lost control of your system on this day. What did you do with this product? Where did it go? This is going to be your part 2, where you are documenting so that you can prove that you corrected the issue, that you prevented that unsafe product from reaching your consumer, and that you have now prevented it from happening again. So, if you are taking this, next slide. If you are doing something like taking this to the landfill or somehow destroying it, you'll want that bit of evidence there. So some of our records that we can use in this instance are going to be recording or referencing directly to our HACCP monitoring record that we lost control of the system. And we're going to have some corrective action procedure forms that are identifying the product. So, what's the lot identifying information for this product, so we know it was diverted or destroyed or processed or whatever we did with it. That deviation description, so in this case, we lost control of our sanitation in our dump tank, so we did not have sufficient sanitation and therefore microbial hazard. Our corrective actions that we took, so we added more sanitizer, we diverted it, what did you do to it? Who made this decision? The person who makes this decision is not your minimum wage line worker who does not have any food safety training at all. Do not put that on that poor person who just wants to show up to work and do their job. This is a food safety manager. This is the owner. This is someone who has the authority to make the decision and not be your scapegoat if this was the wrong decision. So please do not put that on someone who's never had food safety training and does not know why they're making decisions. Why, or that determination of the root cause, so why did this happen? Well, we don't have enough automated equipment, or our PAA concentration, we measured incorrectly because our SOP was incorrect. What actually happened? How do we make sure that we're not doing this again? What caused this deviation? Some of our audit requirements are going to include these records for our preventive actions to prevent that from happening again, and those follow-ups to make sure that we followed those corrective actions. So some of our disposition records, so I'm not interested in how happy or sad your produce is, but what you did with that produce, so your disposition, the reasoning behind it, the number of units, dates, lot codes, any of that identifying information, how it was destroyed, keeping in mind destroying as much as possible. Tossing in a dumpster might not always be an effective way of destroying product because people do dumpster dive. So making sure that you do try to destroy it. If you take it to the landfill, get those landfill receipts. Pictures of you destroying it could potentially be documentation, just something, and who is responsible for that, how it was destroyed, how much of it was destroyed, and all of that can be useful in those records. So in a properly implemented or designed HACCP plan, all of those deviations are going to be discovered and corrected before any of that product leaves the facility. So you're going to have robust monitoring that's going to be catching problems before they have the opportunity to result in product leaving your facility. Monitoring at that CCP is going to allow that corrective action before there's a need to reject or to place product on hold. So in our case, one of the things we might do is say, all right, we lost way too much product because we lost a half day of production with that deviation we had with not having enough sanitizer. We might need to increase how often we are monitoring that system. We might need to make some change to make sure that it's less likely to deviate. We might need to automate that system so we're not relying on someone to remember to go back and add more sanitizer when it's necessary, but maybe we need to automate it completely. So some examples of when some of our corrective actions are going to be needed. Here we have this great example that we just went through. When our monitoring indicates our water sanitation procedures aren't working, we don't have enough sanitizer in the water. Our sanitizer inventory is being used faster than expected, or maybe not as fast as expected. So, our inventory person keeps telling us that we're out of, or we need to keep ordering sanitizer. Maybe we're not using it at the correct dosage. Maybe someone isn't following the SOP correctly. Maybe we need to watch whoever is using our sanitizer to make sure that they're actually doing it correctly. If our pH readings are not in the correct range, particularly important if we're using something like a sodium hypochlorite or a calcium hypochlorite, where pH is going to be something that we're also monitoring and are really concerned about, because our pH is going to directly impact how effective that chlorine-based sanitizer is. If our workers are reporting a problem, anytime that happens, we might need to have a corrective action. Or again, when our monitoring and our record keeping documents are not in good shape or aren't correct. So, if you have any questions, you can direct them to Alexis. Oh, I guess I can take a couple questions. I think I have a couple minutes. But yeah, any questions on this?
Does anyone have any questions?
Oh,
Yep.
I was just going to say, one thing I've seen other than destroying product is people go in and look at water quality. And I would say also be really cognizant of what your critical limit is if you're making that a CCP, because sometimes you can have a far lower critical limit versus your operating limit that you're looking. So designing your programs is sometimes also really important.
I'll try. Okay, so everybody loves to throw this water CCP thing around, but why? Why does it have to be a CCP? Why couldn't it be considered a control point? And if it was a control point, then you wouldn't have had to destroy it. You could have reran it. So why is that never discussed? Why is it always, it has to be HACCP, it has to be CCP? We're produce. We can't kill anything. And no matter what we do, it's not dead. So why don't we put that alternative out there, and why do we just, this is it, done, over?
so you're thinking like a canner right now. You're thinking,
Meat, dairy, juice, all of it. It's a CCP, we're produce. We are
prevent, eliminate, or reduce.
Yes.
So reduce.
By 6 logs, but as a control point, that means if it runs through the line, and I think you're on the HACCP training that I was in, so you'll remember this whole conversation and where it went to. Why is it never discussed that, yes, you can make water a control point instead of a CCP, and that you can rerun it at that point when it is a control point, but you cannot as a CCP because now you have adulterated product? Because we technically can't 100% guarantee that anything we run through that water is safe, as we've seen with every commodity that's run through water and had a recall. So are we really doing industry any help by saying it has to be a CCP? Because let's face it, that's just a little Band-Aid to say, here, we're good. But honestly, are we really? Because it's produce and we're not killing anything.
I think you have to rely on you're reducing. So anytime you're using water in a system, particularly if you're using batch water in a system like this, your best bet is going to be a CCP because you don't have control of that system and you've now lost control of it. So, I mean, that's I think what we landed on in that class that you attended, of we keep these as a critical control point. We are not necessarily able to eliminate our hazard here, but we're relying on that reduction point of it. Yes, question.
My question is not really in terms of a CCP, but I was just going to ask the group. Thank you. We've always used chlorine as our disinfectant in our dunk tank, and then we switched to PAA 1 year, as that's what our Primus auditor preferred. And we had a hard time with the labeling of chlorine. The EPA labeling on chlorine really needs to be updated. But what we discovered when we were dunking or using PAA, particularly in summer squash or soft squash, is that it negatively impacts the quality of the produce. I didn't know if anybody else was having results like that, where the PAA, it literally started to destroy our product. It turned it to just, it fell apart. Even though it was a good sanitizer for the wash water, it completely destroyed the quality of the produce. And so we're starting to have some really negative impacts of Primus pushing higher levels of chlorine now too, or pushing PAA, which are negatively impacting the quality of our stems on our peppers, turning our zucchini into mush. Is anybody else having those issues? But if we're forced to run that high, so now Primus is now requiring 10 to 20 on chlorine, which is affecting.
We might be running up on.
I ran into the same issue with disinfectant and peach in our hydrocooler. If we run too hot, we were running sodium hypochlorite, and bronzing is a big issue in peach, and so we've tried different things. Definitely can't use PP. Yeah, we can't do that. But we went to chlorine dioxide. But I wanted to make this comment. We come to educational sessions and we hear about this process, yet when it comes down to the audit, then all of a sudden we talk about actual numbers. And so I'd love to go to a education session that talks about disinfectants and what levels that y'all think are right, because that's in my opinion, it's kind of up to your, as Wendy was saying, up to your discretion. So if we really want to educate us about having safe produce, then let's talk about what should be in that post-harvest water, what those levels.
In Laurel and face-to-fence, they don't recommend a particular number. Like, it doesn't have to be a hard number. We've done a lot of consulting work with Laurel and Miss Faith, and we switched to PAA, and we did not have we didn't see it hurting the squash or anything, but it damaged our galvanized coils in the hydrocooler. So we switched back to chlorine, and because of, Laurel, would you like to give more of our testimony in that? Because what he said really isn't true, so in y'all's defense, I think it's, and what Wendy's saying, as long as we have our negative evidence of our testing, look at the guidelines, look at the label, but there is no set number.
And we need to get on to the next speaker. So, but yeah, as Courtney said, there is not that set level. And Morgan, do you want to?
Yes.
Okay.
And with that, I will join me in thanking Laurel for her presentation. Thank you. Next up, we have Natalie Dyenson, who's going to present an overview of the National Cantaloupe and Netted Melon Guidance for Food Safety. Thank you.
Good afternoon, everyone, and thank you for being here. Now, some of you in here probably don't grow melons, and you're like, what does this have to do with me? I would say that some of the topics that we'll go through are actually going to have relevance across a lot of different commodities, so I'd encourage you to stay. All right, so why do we have a national melon guidance document? I can tell you that this really came out of outbreaks that happened in the late 2000s. Specifically, there were 4 major outbreaks that occurred between 2008 and 2012. Salmonella and Listeria, some imported, some domestic. But the thing that really prompted action is the fact that the cumulative impact of these outbreaks was 488 people ill, 256 people hospitalized, and sadly, there were 33 deaths. And so once that happened, the industry came together and said, we need to do something about this, especially since the deaths came from domestic product and not from imported product. So a collaborative group was convened. The work of the original, the National Commodity-Specific Guidance for Cantaloupes and Nutted Melons was led by the Fresh Association, or Fresh Produce Association of the Americas, which is actually a group that works with importers from Latin America coming into the United States. The Produce Marketing Association and United Fresh Produce Association, which are the two legacy organizations that then became International Fresh Produce Association, where I work today, and then Western Growers. This was truly a collaborative effort, and there were around 70 experts from industry, academia, and regulatory that contributed to the development. And what's even more impressive is that there were regulatory officials from 6 different agencies across the US, Canada, and Mexico. So it wasn't just a national guideline in the United States, it was truly almost a global effort. And I will tell you, I don't have it mentioned here, but these guidelines were then adapted in Australia. They call cantaloupes down there rock melons. I'm not really sure why. I guess it's because it looks like a rock. But they were adapted for rock melon growers in Australia as well. So why are we updating the guidance now? Well, as you can imagine, outbreaks, guess what? So in 2018 and 2019, there were 2 outbreaks that happened. They were both on cut melons. There were over 200 people ill and almost 75 people hospitalized. And then from 2020 to 2024, there were 3 confirmed and 2 suspected outbreaks, causing almost 600 illnesses, sadly over 200 hospitalizations and 6 deaths. And even more concerning is that most of these outbreaks that happened between 2020 and 2024 were the same strain of Salmonella. So they were seeing the same strain popping up in cantaloupe grown in a specific region here in the United States. And we realized that it was time for us to take a closer look. The other thing is the science has evolved. The science, as you can imagine, has evolved a lot since the original outbreaks happened in 2008. In fact, I think since the original document was written, there have been at least 10 research studies that have been funded by Center for Produce Safety, specifically looking at cantaloupes or processes and things that impact cantaloupes, so that have informed actually processes and technologies that you can use for handling cantaloupes. The other thing is since 2013, as you can imagine, there have been a number of regulations that have been published. So we have the Produce Safety Rule. The original rule came out in 2015. The Preventive Controls Rule came out slightly before that. You have the Ag Water Rule, and then the updated Food Code. And I mentioned the Food Code because we are going to talk a little bit about retail and food service here later in the presentation. So, again, we are having it be a collaborative effort. The work is being led by International Fresh Produce Association and Western Growers again. We have a broad representation of experts, and we started this process of trying to organize and identify experts that want to participate, started in late 2023. We put out a really broad call for participation. One of the things that's really important for you all to know is that we wanted to make sure that we had growers from different growing regions, because obviously the way you grow melons in Arizona is not the way you grow melons here in Georgia. We wanted to make sure that there was representation of both domestic and international growers, because we still have international imports coming in of melons from Mexico, Honduras, and Guatemala. And we also have representation of all sectors of the supply chain. And that's something that's a little bit different this time, where we're really emphasizing that. We did have folks from multiple sectors of the supply chain, but you're going to see that as an impact in this final product that'll be coming out later this year. The project was kicked off in April of 2024 with an in-person meeting, and work began shortly after that. So let me give you a little bit of an overview of the process that we're taking this time. So we did expand the guidance to include the end-to-end supply chain because there's been a lot of research that's happened. Actually, Laura Strawn's not here, but she did a study that was published or sponsored by Center for Produce Safety that actually looked at Listeria contamination throughout the entire supply chain from harvest all the way to retail. And so we know that there are contribution points and things that can exacerbate challenges in other parts of the supply chain, not just at the grower level. And so we felt it was time that we illuminated that and put that into guidance for the industry. We also divided the volunteers into 3 groups. We have a group that's working on growing and packing, which is pretty much what the existing document was today. That was being led by Western growers. And then IFPA is leading the other 2 groups, one looking at fresh cut processors and the third one looking at retail and food service. The other thing that we did a little differently this time is instead of saying, this is what you need to do, we're presenting things as a continuum. So there is the updated version will have things presented as good, better, best, where good is this is the regulation and you have to meet this, but best being that gold standard so that you can see this as a continuum as you have your operation and you can look for ways to improve over time. Sometimes that's from an auditor recommendation, sometimes it's not. There are some advantages to the way that we're doing it this time, but there are also some limitations I want to acknowledge. So first but foremost, having the expanded document showing the end-to-end supply chain contribution, it allows transparency of practices across the supply chain, which is fantastic. It's kind of illuminated some programs which cut across all segments. So for example, things like worker hygiene, traceability, cleaning and sanitation, just to name a few, are things that apply regardless of where you sit in the supply chain that will really have an impact on the safety of products. So we're able to then see that and create consistencies throughout the document across those different sectors. The challenge, however, or limitation is that all 3 sectors that we're talking about here, growing, packing, fresh cut operations, or retail food service, they're all governed very, very differently. So the regulations aren't necessarily aligned. So you've got the growers and pack houses that are under the produce safety rule. You have the processing operations that are under the preventive control rule. And in theory, those are harmoniously aligned in theory. And then for retail and food service, they are actually regulated under what's called the FDA Model Food Code. And what's interesting is whereas FDA has inspection and oversight that they can subcontract out to the states for produce safety rule and for preventive rule, FDA actually doesn't do any retail or food service inspections. Those are 100% done at the state level. And the FDA creates this model food code, which is a fantastic guidance, but then the states decide, do I want to adopt that in whole or in part? And do I want to keep the food code I'm working on from 1997, or do I want to adopt the new changes that have happened in 2019 or 2018 or 2022 or whatever? So there's a lot of inconsistencies, and that's creating some challenges. So what we've done is we've modeled all of the recommendations in the document off of the most recent version of the food code, which is the 2022 version. I will also say that there are some interesting things that in the model food code right now really doesn't mention a lot about fresh fruits and vegetables and fresh processing of fruits and vegetables, but they are looking at potentially a proposal to go in front of the next Conference for Food Protection, which is the convening session where they decide what goes in the food code. And they're looking at having additional controls and kind of changing what they consider to be, we call it time temperature control for safety now, so potential hazards. So this is something that could create some inconsistencies in the supply chain as well, that at IFPA we've been working on and making sure that the decisions will be in the best interest of the industry based on risk and science. And then last but not least, I would mention that there's a lot of confusion on how terminology is used, not just across the industry or within regulatory. So for example, you'll hear the words risk and hazard. Some people use them interchangeably like they're the same things. They're 2 very different things. And that's challenging because in the way some of the regulations are written, they are written so that those terms are interchangeable, but that's not the practical application of how they're used in the industry. I think another example is disinfection and sanitizing. There are actually definitions that say this is what disinfection means and this is what sanitizing means, and they're different, but yet they're often used interchangeably. So we're trying to address that in those documents too, to provide clarity for the industry. So, group one. This is the growing packing group. What they've done is they've taken the document that we've had, and it's still structured as guidance, and it's not very prescriptive. Think of it more of it as a framework. If you have this happen, you need to think about this, versus saying, if you have this happen, you have to do this. Because that was very important as we started talking to growers from the different regions. It's clear that practices are different, and this document needs to be able to be flexible so that growers can see how they can adapt it to their operation. They have updated the document to align with the produce safety rule. Since the original document was produced before the produce safety rule was finalized, there were some modifications that needed to be made there. And they have actually also updated some good agricultural practices and good handling or harvesting practices as needed to reflect the latest science. The majority of the updates were actually in 3 specific areas, and this is where the bulk of the change comes, and there's a lot more meat and detail here. These are in ag water, environmental monitoring, and traceability. So for the ag water section, they've updated it to align with the new ag water rule that came out this past spring in 2024, May of 2024. There's a lot more detail than in the earlier version, helping to provide practical examples and guidance. There are some tables even that says, if you do this, you might want to consider that. And so it's a lot more, I think, user-friendly, and that was the feedback that we heard from the growers that were involved in this. For the pack house, they've expanded the focus in the document on the pack house and cooling operations, and specifically introduced the concept of environmental monitoring. This is something that is not required under the produce safety rule, but it is required under the preventive controls rule, but it's strongly encouraged under the produce safety rule. And so we've introduced that so that growers and people using this guidance can understand why you do it, when you do it, how you should do it, understanding the mechanics of some of the choices that you make around hygienic zoning or where you're sampling, how often you're sampling, things like that. And then last to this section was a pretty significant update to traceability to align with the traceability rule, Rule 204. And there's a lot of several pages of detail drilling down into the key data elements, the KDEs, as they apply to each of the CTEs, critical tracking events that are outlined by FDA. So it's a really great table that makes it very clear, if you're doing this, this is what you have to collect and this is what it looks like. For the fresh cut processors group, the content that is specific to fresh cut processors is new for this version. So we always had some of this information in there. It was kind of generally listed under facilities in the old document. And now we're kind of teasing out pack houses and cooling operations from fresh cut processing to add some additional clarity, because there are some unique nuances on both sides. The information, again, as I mentioned, it's being presented as a good, better, best to show operators that pathway to excellence. What does it look like? I can do this today and I'll be in compliance with the law, but as I continue to grow the food safety capacity in my operation, where do I need to go? And that's really important because that can help you as a grower kind of plan and budget, quite frankly, for changes that need to be made. We also made sure that the document, as represented, was aligned to the elements of the preventive controls rule. So that means incorporating like what's it called? Food safety plan. There we go. Sorry. Late in the day, my brain glitches. And things like that. There are 3 main focus areas in this document. There's really going to be a showcase around wash water, traceability, and allergens and labeling. And so for the wash water, we've really strengthened the section on wash water, providing more detail, again, as it is unique for the fresh cut processors type operation. And we've expanded traceability details to align more closely with the Rule 204. Additions that are new that weren't in the previous version, would be the introduction of the concept of allergens. And you might say, well, the 9 allergens recognized in the United States aren't in fresh cut fruits and vegetables, right? But the challenge is a lot of the fresh cut operations do a variety of different products. They're multi-use facilities, and because of that, they really need to be thinking about their process flow, their storage, and their handling practices. In addition, when you're doing fresh cut fruit, you have to have an ingredients label. So you have to list on there in predominance the types of fruits that are in the bowl, because not everybody recognizes them. So going over that and adding some detail around that as well. The last group is the third group. So retail and food service, again, this is specific content that's new in version 2.0. Again, we're presenting it as that good, better, best. And everything has been aligned, as I mentioned earlier, to the food code for 2022 requirements. So the major changes here is that they've strengthened the section on a written food safety plan, taking a kind of a cue from the preventive controls rule. They've expanded HACCP and HARPC details to be more specific for retail and food service. And I think probably most importantly, they've put a lot more detail in there on supplier control and verification plans for retail and food service. Because the reality is, if the cantaloupe isn't safe when it gets to the retail store, it's not going to be safe when they process it at the retail store. Additions to the content would be the concept of the hazard analysis in the written food safety plans. So hazard analysis wasn't something that was being evaluated at retail. We've included some handling and process flow for fresh cut. So there's a nice little diagram that kind of shows if you're going to be processing melons, don't do it in your meat department. If you do it here, things to think about as far as process flow. And then we've also incorporated the concept of preventive controls for retail and food service. So where are we with this work? Group 1, the work will be finalized at an in-person meeting next month. And so they will all be meeting, I think, in Arizona to go through the final details and get that all squared up. Group 2 and 3, they got started a little bit later because we had a few personnel gaps at IFPA, but I'm happy to say we're fully staffed. And the work is now in the final stages, and we expect that to be wrapped up by late February or early March. The combined draft document then from all 3 groups will be released for public comment, and I cannot stress this enough. If you have any, this is something that could potentially impact your operation, we really, really, really want candid feedback. We want to make sure that this is a practical document that makes sense, that can be used. And so when this is released for public comment, we would really encourage everyone to take a look and make comments on the content and the changes that have been made. While the comment period is going, the work groups will sit down, and this is something that's new this time for this approach. In the past, what we've done is we've said, here you go, here's the best practices guidance document, yay, it's posted on our website. This time we're going to be a little bit more intentional, and the work group will sit down and develop a communications plan, a plan for dissemination of the information, for education on the materials, and also for implementation. So we're trying to help take it to that next step and provide support for the industry on how you actually then take this document and make it a reality in practice. Once the comments are reviewed, the document will be finalized and released per the communication and dissemination plan. And then last but not least, I would say expect to see webinars and training courses, as well as some follow-up surveys, because we're really trying to make sure, is this working? Is it not working? Is it adding value? Where does it maybe have some gaps so that we can figure out how we drive continuous improvement in this process in the future? So that is it. And I did it in 20 minutes, just like I was supposed to. Woohoo!
Excellent. Thank you, Natalie.